So, oh, that's already passed. So, assignment 6, that's going to be due on Wednesday next week, and wait, that's next. Right, yeah, next time's the 14th. Yeah, and then exam 2 will be on chapter 4 and 5. Wait, what did I? Not this Monday. What did I write last time? Wait a minute. What did I do? Right, so that's due Wednesday, 4/21, like I was saying. And so why did I write 4/12 last time?
You wrote that the exam 2 was going to be today?
Oh, shoot, that was... Oh, my goodness. On chapters 4 and 5, why did I think chapter 6 was supposed to be on that? Okay. Well, obviously it's not going to be today. It's going to be on Wednesday. And so we'll do that next time. I apologize. I don't know why I did that. So this Wednesday. And therefore, I need to have those assignment number 5 back to you today. Okay. I apologize. I'm lost for some reason. I thought the chapter 6 was supposed to be on this exam. No, that's on the final exam. All right. So we'll do the exam 2 on Wednesday, and so today we'll just continue with chapter 6. Okay. I don't suppose anyone has any questions on assignment 6 at this point. Then I did get a couple people sending in, preliminary drafts of their homework for assignment 6, but not too many yet. All right, so last time we went over this problem that we were proving using the first principle of induction. And the first few problems that we did using the first principle of induction, they involved equations, or inequalities with certain, sort of simple identities, like this one here, problem number 1, right? Simple identity, and problem number 2, just a simple inequality. But things get a lot more interesting when you start getting into more kind of geometric things. So last time we went over this problem. If a collection of n lines collection of n lines, call it L, in the plane is in general position when every pair of lines in L intersects, so no two lines are parallel, but no three lines intersect at the same point. So every pair of lines intersect, but you never get three lines intersecting like that. So we want to prove that a collection L of n lines in general position always divides the plane into n squared plus n plus 2 over 2 regions. So that is the predicate Pn, the predicate that depends on n. Predicate logic statement that depends on n. So n lines divides the plane into that many regions, n squared plus n plus 2 over 2 regions. Now, of course, being in general position is necessary, because if you're not, right, three lines not in general position, like that, gives you 6 regions, whereas 3 lines in general position gives you 7, right? So the number of regions changes depending whether or not you're in general position. But as long as you stay in general position, then the number of lines is a constant. And that's interesting because, when you only have 2 lines, any arrangement of 2 lines essentially looks like that. I mean, you can rotate this line, so that the angle between them is really small, or the angle between them, is 90 degrees all the way around. Whatever the case might be, but 2 lines essentially look like that, up to shifting and rotating the lines. 3 lines, they always look the same. It always looks like this. I mean, again, you can always kind of shift the lines a little bit. Angles change or whatever, but it's always a triangle surrounded by these other regions. 4 lines, it always looks like this. But things change once you get to 5 lines. So 5 lines, it could look like that. All right, have this nice, neat little star, 5-pointed star in the middle. Or here, 5 lines could look like that. There's no 5-pointed star in there at all. But even though topologically they're different, geometrically they're different, the number of regions is still 16. So, right, which is if you plug 5 into that polynomial. 5 squared plus 5 plus 2 over 2 is 16. So the base case, one line gives you 2 regions, obviously. And this expression, this polynomial with n equal to 1 gives you 2. So that's what you wanted. And then in the induction step, you assume that any collection of n lines in general position divides the plane into n squared plus n plus 2 over 2 regions. So that's the assumption, right? We're trying to show that Pn implies Pn plus 1. Right? Pn is this statement here. Any collection of n lines in general position divides the plane into n squared plus n plus 2 over 2 regions. So assuming that's true. Now, show that any collection of n plus 1 lines in general position divides the plane into this many regions, n plus 1 squared plus n plus 1 plus 2 over 2. All right, so assuming n lines does the job we want it to, show that n plus 1 lines does the job we want it to. So, before we went any further, we noticed that this polynomial, when you simplify it, is this, n squared plus 3n plus 4 over 2. So you take n plus 1 lines, so say that L has n plus 1 lines. Okay, by the way, so this proof is very similar to the proof that you will do on assignment 6, number 3. So assignment 6, number 3 is again about lines in general position. All right, it's right here. So, we want to go over this proof carefully and understand this proof. So let L be some collection of n plus 1 lines. Take away one of them. Take away H. So L's got n plus 1 lines. Take away one of them, that's H. So you got n lines left. And they're still in general position. The general position doesn't, it's not an existence type statement. It's a universal type statement. Every pair of lines in L must intersect, and no 3 lines in L intersect at the same point. So if I take away one of those lines, it still satisfies that property. So this is still in general position. So by the inductive hypothesis, this arrangement of lines divides the plane into the requisite number of regions. N squared plus n plus 2 over 2 regions. So now line H, let's put it back in. It intersects the other n lines at 1 point each. See that? So there's line H, and here's all the other lines. There's n of them. And they intersect H at 1 point each. Why? Because every pair of lines intersects. So you get one intersection point for each line. But no 3 lines intersect at the same point. So the intersection points for the n lines are unique or distinct. So you have that many intersection points with the other lines. So H, it's passing through a region each time, a new region, every time it passes through one of the lines. So here's a region. Here's a region. Every time it goes through one of those n lines, it goes through one of the regions from before. So, how many regions did we have? Okay, so of the n squared plus n plus 2 over 2 regions defined by L minus H, H passes through n plus 1 of them. Region 1, region 2, region 3, 4, 5, 6, region n minus 1, region n plus 1. Right? Here's the numbers 1 through n, and then, if you look at the spaces in between those dividers, you get n plus 1 regions. Right? So 0, 1, 2, 3, 4, up to n here, if you want. So it passes through n plus 1 of those regions. And each time it goes through a region, it divides it into 2 subregions. So each region that it passes through gets cut into 2. So a total numerical gain of n plus 1 regions. It passes through n plus 1 regions and replaces each with 2 smaller regions. So you lose n plus 1 regions and you replace them with 2n plus 2 regions. So for a total gain of n plus 1. So L defines this number plus this number of regions. Right? We had this many before, and then we gained a total numerical gain of this many regions. Add that together, and you get the number you want. N squared plus 3n plus 4 over 2. So, in the homework, for assignment 6, number 3 here. An arrangement of L lines in the two-dimensional plane is in general position when every pair of lines intersect and all 3 lines intersect in a common point. The collection L divides the plane into regions. Some of the regions are bounded by polygons, and some of the regions are unbounded. Use the first principle of mathematical induction to show that the number of bounded regions is this much. N squared minus 3n plus 2 over 2 regions. So let's go back to those pictures we had before. All right, so here is 5 lines in general position. So for problem number 3 on assignment 6, let's take a look at the 16 regions here given by 5 lines. Oops. Alright, so we have 5 lines and bounded regions. We got 1, 2, 3, 4, 5, 6. 5 lines and 6 bounded regions. Right? So n equal to 5 lines, 6 bounded regions, and then n squared minus 3n plus 2 over 2, with n equal to 6, or n equal to 5, is 25 minus 15 plus 2 over 2. So that's 25 minus 15 is 10, plus 2 is 12, over 2, all right, which is 6. So there's the number of bounded regions. Okay, so now the proof for this is nearly identical to this one. Nearly identical to the proof here. Okay, the only difference comes in, well, we're using a different polynomial expression, of course, but when you're adding this line back in. Okay, you're adding that last line back in. So let's take a look at how it works. Okay, so here's 4 lines, right? And here are the bounded regions. Right, that's a bounded region. That's a bounded region. And that's a bounded region. There's just 3 of them, right? Now, add the 5th line back in. Right, so how do the bounded regions increase at each step in the inductive process? All right, so here's 4 lines, and you've got these 3 bounded regions. What do you notice about the bounded regions? Right here and here. What do you notice about the bounded regions? Like as where they are. Where are the bounded regions in these 2 examples?
In the center.
They're kind of in the center, and the unbounded regions are on the periphery there, right? So like if you've got 4 lines here like this, and then you want to increase to 5 lines. I should make it a different color. So I'm going to take the 5th line and put it in here. 5th line. Where are the bounded regions increasing? Right, here's this bounded region got cut into 2. This infinite region got cut into, right, a bounded one and an unbounded one. And then this unbounded region gets cut into a bounded one and an unbounded one. What do you notice about the 5th line and the increase in the bounded number of regions and the increase in the bounded regions as far as creating new bounded regions goes? Where are new bounded regions happening with with respect to the 5th line?
Below it.
Well, there's one above it right here, yeah? Here, this bounded region. Yeah, I guess that's an interesting point. But you know, I mean, here, like this blue bounded region here got cut into 2 smaller ones, right? It got cut into 2 blue bounded regions. The unbounded regions got cut into a bounded and an unbounded region. And then these unbounded regions here are just cut into 2 bigger unbounded, or 2, I don't know, subregions, 2 unbounded subregions. Where are the bounded regions, new bounded regions occurring with respect to that line? Along the what? Right. Look at the segments created in the purple line with the 4 intersection points.
Could you say along the horizontal axis? I don't know. Like
part of it.
I guess above and below it.
Well, this is above and below, but they're unbounded, right?
At the intersection points.
The only place at the so I mean there's there's infinite segments on the 5th line and finite segments, right? The new bounded regions are occurring along the finite segments, right? All right, so here's the 5th line. Yeah, that's the right color. All right, here's the 5th line. That's the wrong purple, but it's all right. Here's the 5th line, right? And here are the intersection points. Right? Intersection 1. Intersection 2. Intersection 3. Intersection 4. Right? This is an infinite segment. Well, infinite ray. Right? Finite segment. Finite length segments. Well, let me do it this way. So infinite length ray. Infinite length rays at the beginning and at the end. Right? And these are finite length segments. 2, and 3. So suppose I have a finite length segment. Can a finite length segment take an infinite region and divide it into 2 infinite regions? Can a finite segment,
Could you say that one more time?
yeah, can a line segment of finite length divide an infinite region into 2 infinite subregions?
I'd say that doesn't sound nice.
No, no, totally can't. A finite length segment can only take a finite region and divide it into 2 smaller finite regions, or an unbounded region and divide it into a bounded region and an unbounded region. Right? Finite length line segments either cut a bounded region into 2 bounded subregions like this. So you have some kind of bounded region like that, and then you take that bounded region and cut it into 2 smaller subregions, like so. Why does that look terrible? Leave out the color. Purple go. Right, it takes a bounded region and divides it into 2 bounded subregions, or cuts a unbounded region into 2 subregions, one bounded, the other unbounded. Right, so if you had some unbounded subregion here, or unbounded region, like that, right, unbounded, right, and then you put a finite length segment in it to divide it into 2 subregions, well, what you're going to end up with is something like this. Right? This is bounded, and this is not bounded. Also, the infinite length ray cannot create a bounded region, obviously. Cannot be on a bounded region at all. Right? right? I mean, if the region is bounded by a polygon, no side of that polygon is going to have infinite length. So every time you add a new line to your arrangement of lines in general position, the number of bounded regions increases by 1 for each finite line segment. Therefore, every new line in general position increases the number of bounded regions by 1 for each finite length line segment it gets divided into. So here, with this problem of, what are the, I'm trying to say here, the number of bounded regions created by n lines in general position. I mean, you're just working with a different polynomial expression. Where is it? N squared minus 3n plus 2 over 2. So in the inductive hypothesis, the number of regions you will have would be this. And then when you add in a new line, the increase in the number of regions, well, the first and the last region don't matter anymore, because they can't create new bounded regions. Only these create new bounded regions. Right? So whereas the increase in the number of regions by the n plus first line up here, right, we threw in that new line h, and the number of regions increased by n plus 1. So when we're talking about bounded regions, the number of bounded regions increases by 2 less than that, which is what?
N minus 1.
N minus 1. It's the only difference. It's the only difference here. Okay? So that's like a really, really neat application of induction. It can be described using a process actually different than induction, although it's a really nice example for doing induction. The process by which, it's not a process, but the way of describing the number of regions, bounded and unbounded, given by n lines in general position, the way of describing it, not using induction is better, because it's more descriptive. But it's a really nice example of how induction works. And, as far as arrangements of lines and arrangements of planes and, so a line, in 2 dimensions, it cuts 2 dimensions into 2 regions. A plane in 3 dimensions cuts 3-dimensional space into 2 regions. More generally, in n-dimensional space, so in 20-dimensional space and a 19-dimensional subspace, it divides it into 2 regions. I'm not sure how useful the multi-dimensional analogs of these things are, but anyway, I mean that's the idea. Like if you have a space of dimension n, a space of dimension n minus 1 cuts it into 2 regions. And the person who really was the first to study that in depth to study this topic in depth was actually the guy that I did my doctoral dissertation with. He was my dissertation advisor. His name is Tom Zaslavsky, who's actually still working at 75. And I keep asking him, why don't you retire? But he doesn't want to. Anyway, this is his. So this is one reason it's a favorite topic of mine, because when I first met him and I asked him if I could work with him, he said, well, okay, yeah, why not? Why don't you take a look at this? And I started looking at it. And it's not what I eventually ended up doing, but nor is it something I've ever really worked with, but it's still a favorite topic of mine. All right. So, first principle of mathematical induction. There is also a second principle of mathematical induction. The second principle of mathematical induction, it's equivalent to the first, logically equivalent to the first, but somehow it's more powerful. Now, really, when you do induction, you're actually always using the second principle, although the first principle pedagogically is easier to present. But here's the second. To show that for all n, P of n is true over domain D, which, as before, is a set of consecutive integers with the smallest starting point. It suffices to show that P of 1 is true. Again, that's called the base case. And 2, for every n, P1 and P2 and Pn altogether imply Pn plus 1 is true. And that's the inductive step. So, what's intuitively the idea here with the second principle? I mean, in practice, the only difference is the induction hypothesis. So, in the second principle of induction, the induction hypothesis is this right here. P1 is true, and P2 is true, and P3 is true, and all the way up to Pn, that is the induction hypothesis, rather than just Pn, as in the first principle. Of induction. So in the first principle of induction, you assume Pn is true, and then you show that Pn plus 1 is true. In other words, step n plus 1 follows from step n. Step 3 follows from step 2. Step 4 follows from step 3. Step 5 follows from step 4. Step 1000 follows from step 999. So on and so forth. Every step follows from the step before. With the second principle of induction, that's not what you're getting at. With the second principle of induction, step 5 follows from steps 1 through 4. Step 100, it doesn't necessarily follow from step 99. It follows from some step that came before. Every step follows from some step that came before, or some several steps that came before. And the first example one always uses is the following. I've never seen anyone not use this at first, but I've got plenty of good examples. This is just, a classical one. Every integer n bigger than or equal to 2 is either prime or a product of primes. Every integer n is either a prime or a product of primes. I mean, you know this, right? I mean, every integer is either prime or a product of primes. And maybe you haven't thought about it before, but yeah, I mean, obviously it's true. You just keep splitting it up into integers until you get, prime. So like 100 is what? Is 25 times 4, right? And 25 is 5 times 5, and 4 is 2 times 2. Let me do it this way. 5, 2, 2. So 100 is equal to 2 times 2 times 5 times 5.
Factor trees.
Oh, okay, factor tree. Anyway, the fact that 100 is prime follows from the fact, the fact that 100 can be written as a product of primes follows not from the fact that 99 can be written as a product of primes. It follows from the fact that 25 and 4 can be written as a product of primes. So notice that. That the fact that 100 can be written as a product of primes follows from the fact that both 25 and 4 can be written as a product of primes. Okay, the fact that 99 is a product of primes is completely unrelated. It is completely unrelated. Right? Here's 99. What's its factor tree look like? Well, it's 9 times 11. 11's prime. And 9 is 3 times 3. Right? So 99 is 3 times 3 times 11. I mean, what's that got to do with the fact that 100 is 2 times 2 times 5? I mean, other than the fact that you're using, the factor tree, nothing. I mean, there's no primes in common here. Right? So the fact that 99 is a product of primes follows from the fact that 9 is a product of primes and 11 is a prime or product of primes. 98 has nothing to do with it. Right? The fact that 90, what's 98? 98 is 49 times 2, so it's 2 times 7 times 7. So on and so forth. So here's the proof. Base case is n equal to 2. Well, 2 is what? 2 is prime. Done. Induction step. So in the induction step, we want to show, so we're starting at 2, by the way, P2 and P3 and Pn implies Pn plus 1. The main challenge in applying the second principle of induction is how do I say the induction step? How do I say the induction step? Notice that there's only one variable here. There's the n. Okay, but in order to say the induction step properly, you need to introduce another variable, k. Okay, so assume, so here's the inductive hypothesis. Assume that for every k in the set from 2 to n, that k is either prime or a product of primes. So the new variable k is introduced in order to write the induction hypothesis. In order to properly write the induction hypothesis. So here's the induction hypothesis right here. So we want to assume that 2 is prime or a product of primes, 3 is prime or a product of primes, 4 is prime or a product of primes, 5 is prime or a product of primes, dot, 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 n minus 1 is a prime or a product of primes, and n is a prime or a product of primes. So all these numbers from 2 to n, they're all either prime, each one is either prime or a product of primes. And now, what is the target conclusion? Show that n plus 1 is either prime or a product of primes. Alrighty, well, if you want to show that something is either A or it's B, assume it's not A, and then go from there. So we write like this. Well, if n plus 1 is prime, then we're done. Okay, if n plus 1 is not prime, then, right, n plus 1 must be equal to A times B, where A and B are where? I mean, a number that's not prime, you can break it into a product. Right? It's divisible by something other than 1 or itself. Right? So if it's divisible by something other than 1 or itself, right, you can break it up into a product of that divisor and the stuff that's left over, the quotient. And that divisor and quotient lie where? Where are A and B? Can they be bigger than n plus 1? No, they have to be less than n plus 1. Right? They have to be in this set, nor can they be 1. They have to be between 2 and n. So by the induction hypothesis, right, A is equal to P1 to Pn, and B is equal to Q1 to Qm, or I shouldn't use N, PS, Q1 to Qt, where each Pi and Qj is prime. So n plus 1 is equal to A times B, which is P1 to PS times Q1 to QT, which is a product of primes. Okay, so that's the first example. I'll have a nice geometric example for you next time. Sorry, I don't know why I was so lost. I will get the homework to you this afternoon, and we'll have the exam on Wednesday. So I mean, you got another couple days to study if it's worth it to you, if it's helpful for you. Excuse me. All right, email me with any questions or concerns about that. Okay. All right, everybody. Have a good day.